Sorry about that technical difficulty. Unfortunately, the audio kept working, but the video did not. So for the last 10 minutes of the lecture, if you listen to the other lecture, you'll hear me talking, but you won't be able to see the screen. So I'm re-recording those last 10 minutes. Again, if you want to have the video component or the slides that we're talking about, this is just a redo. So it's the same material heard twice. This allows you to see the screen. Okay, so I apologize for that mistake. So where we left off at around the 32-minute, 10-second mark was at the conclusion of the material we were covering in this particular slide. We had discussed the different depths of the water and how that translates essentially to the water hitting or not hitting the bottom, being in deep or shallow water. Ultimately, what's happening is not only are we changing the shape of the wave, these orbits, to the peaks, to an actual break and ending. Why does this ending occur? Like that's what we were getting to at the very end where that audio and video had the little problem. But what you're going to notice, and most importantly, is this little arrow here that goes back and forth. Right? What you're seeing is there's an energy in this direction. In other words, water being pushed toward the shore. But there's also and equally an energy to restore it, to slow it down, to place it flat. And you'll notice on the opposite side there is flat water. We call that the disturbing force. Okay, that's what's causing a wave, and we went over all the different types of disturbing forces. But we also now need to make sure that we understand that there's a restoring force. The restoring force is moving in the opposite direction, attempting to make that water flat. Why? Because the energy being pushed and being pulled back become equal, and you essentially have nowhere for the water to go. The tug of war has become equal. What is being pushed forward and what is being pulled back become equal. So again, the wave stops. That happens in the surf zone, and that happens at the shoreline, literally right where you're sitting on your towel watching the water. Remember when I showed you this figure, and as we've been talking about this for the past 10 minutes or so in the other video and now this one, what you're essentially doing is summarizing what happens as a wave or what happens when a wave approaches shore. So let's just go over that summary quickly and then look at a couple of more slides that are going to highlight this one more time before we move forward. Okay. So what happens when a wave approaches shore? A deep water wave feels the bottom, right? It gets to that transitional zone. When it becomes transitional, we then know that it's going to become a shallow water wave. Once it becomes a shallow water wave, we know that it ultimately is going to break. Where is it going to break? Shore, right? Because the disturbing force and the restoring force are acting in opposition to each other at the shoreline. But what physically happens to the surface layer of the water within our wave component? Now, here's terms that you remember when we did the anatomy of the wave in the beginning, right? We talked about what an orbit is. We talked about what a crest is, about the tops and the bottoms or the highs and the lows. And then ultimately the velocity becomes critically important as well. So what we're saying is that orbits become elliptical. Eventually they become peaked. The height increases. But ultimately, look how skinny these wavelengths are getting. Okay? Because we know our disturbing force and our restoring force are acting in opposition. So the wave must slow down. The energy ceases. It's also happening because, of course, remember, depth of the water below it starting to trip it up, going from a deep water area to a shallow water area. So of course the wave has to slow down. You're going to notice that that's happening as this increases. That is because the wavelength is decreasing. Okay? So you have a bigger wavelength here out in the open ocean than you do here in the surf zone. There's a couple of more slides that highlight all these exact same points. Again, some people have different visuals and like to see things in different formats. So I like to show you essentially the same image multiple times. What I like about this one is it looks like little marching soldiers, right? Perfectly in unison, perfectly in parallel with each other. Those are the crests of each corresponding wave, right? So this would be the wavelength in between each one, okay? So when you're in the open ocean, the wavelength is wide. When you get closer to shore, the wavelength becomes less. Why does it become less? Because your crest gets higher, the height of the wave increases. Why is that happening? Because the depth of the water is going from deep to shallow. And most importantly, the disturbing force and the restoring force in the surf zone are acting in opposition to each other. Another way of looking at the same figure, again, is showing us that within the surf zone, okay, once we've passed the transitional zone and we're in a shallow water wave, we have a change in height, we have a change in wavelength, and we have a physical change in description of what the wave looks like. Orbit, elliptical, pointy, pointy, and broken, breaking in the direction to which it's being pushed. Why again is that happening? You go from a deep water to a shallow water and shallower because of course you're hitting the shoreline. So in summary, just one more time, how the wave breaks at shore is that the wave becomes too high for the height of it, right, for its wavelength, and the depth of the water that's underneath it, so the wave must ultimately break. Remember, that's how we calculated a deep water wave versus a shallow water wave. You took the wavelength, divided it by 2, and compared it to the depth. We're saying that at the shore, if you take the wavelength, divide it by 2, and compare it to the depth, that number will be greater. There's literally nowhere for that water to go, so it breaks. Again, that's also happening because the disturbing force and the restoring force are acting in opposition to each other. The surf zone is where that happens. And you'll remember this because if any of you have ever been in the water and you stand essentially with your back to the land behind you, right, looking out into the open ocean, or conversely, if you're coming out of the water, looking at the beach, same thing happens. Your feet get pulled out from underneath you, right? It seems as if you're being tripped up and that the sand is kind of building these mounds. That's what's happening. The waves, the energy that the wave is moving toward the shore, it's actually acting almost like a little scooper, like a bulldozer coming in and trying to literally remove that sediment from that location and pull it back out into the open water. But it never really happens because simultaneously you're getting hit with a wave behind you, which is restoring that same material that was being lost. That surf zone becomes a region of very high energy because the two energy components are acting in opposition to each other. One more slide that helps you understand, I hope, how that velocity is occurring, right? So remember, if the energies are working in opposition to each other, and ultimately we have a decrease in the total energy. It's critically important to remember that. So you're going to have less energy here and here from a total perspective of the wave being pushed. Okay, what I would like to do before we move to the end, again, we just have a couple more slides to go. I want to remind us of a topic that we covered earlier on in the first portion of the waves lecture. The second half of the material that you're going to cover in section 2 of the course is tides. Okay, so right now we're talking about waves. The next lecture you're going to have next week is tides. So tides, by definition, is a periodic rise and fall, okay, essentially of the water surface. Now we know that a type of wave is a tide, a tidal wave. Okay, what's causing it? Gravitational push and pull of the Coriolis effect that you learned in the atmospheric circulation. So we obviously can see that there's some sort of connection between tides and waves. What we don't know ultimately yet is what that connection is. Well, what I'm going to introduce here is what that connection is, and this is where we'll start the tides lecture next week. Okay, so getting back to the slide we just left off from. There are two types of interference that we're going to introduce. And again, these are related to waves, but because of how the tides, the periodic rise and fall of the water surface, being pushed and pulled toward the shore, how that connects to the Earth, Sun, Moon interaction that you'll learn next week. Right now, it seems a little complicated. Next week, this will make perfect sense. And I think when I show you this figure coming up in a second, that'll also help you to understand. So remember, a tide is a type of wave. Okay. Interference, similar to constructive and destructive interference, where we talked about the disturbing force and the restoring force, these interferences can work to collectively better or to collectively stop, lessen, or slow down, or destruct. So the two types of interference that we want to introduce are called destructive and constructive interference. First one that we're introducing is destructive interference. This is a cancellation effect, right? Means we take away. So when the wave crest of one wave works with the trough of another wave. In other words, if this is your high point, another wave is coming by and this is the low point. What do? One subtracts from the other and you end up with essentially a flatter water surface. Conversely, if we have constructive interference, this is an additive. This means that the crests are going to match. So instead of this image, which I just drew on the last screen, okay, that's destructive, constructive looks like this. And the next one also matches. So what do you get? A high height and a high height. These collectively give you your highest high water or your highest crest. This is the figure that I was, and there's one more after this that I was highlighting that should help you understand the concept of these two types of interference. Remember, constructive is to add and destructive is to take away. So here we see that our crests match up. So we have our highest wave height. Here we see that our crests and troughs do not match up. So we have our lowest heights. What does that mean from a water perspective? Well, it means that you're either going to have high heights, low heights, or mixed heights. That's when you kind of have in mixed tides, for example, that's when you have highs and lows being pushed and pulled in opposite directions. And so the surface of the water is not as, the intervals are regular, the actual heights are not equal. You'll notice that both of these are roughly the same height, and the troughs would therefore be roughly the same low. So this becomes your high tide, and this becomes your low tide. High tide, low tide, right? That's what that's showing you. In this case, your highs and lows can be mixed in different locations. When we introduce tides next week, we're going to be using these two terms of constructive interference and destructive interference to actually say if the sun and the moon are working together to create the tides, you'll have constructive interference and you'll have your highest high tide, like a full moon, for example. If the sun and the moon are not in alignment with each other, that's two celestial bodies that are acting in opposition to each other, it will offer us destructive interference and you'll have your lowest wave height. That's how tides and waves are connected. So next week, when you go ahead and listen to the tides lecture, you want to remember this last component as the introduction or the launching point or the link between how waves and tides